Okay, in our second video, we've shown that how to find the intersection points of the line cutting the quadratic graph, namely alpha and beta. And we've got the point by using Desmos. Okay, here's the Desmos we've done in video 2. And also, we use the integrals to find the free areas. Okay, and you can use the fourth integral to check whether the sine area is really 0. So what I'm going to do now is to generalize the results from part B for all the m. We understand that for part B, it's only for the gradient m equals 0.1. But actually, since we know that gradient can be from 0 to 1.3, so that means you can have different values of m. And of course, that means different value of c, and so the different equation of the linear graph. Alright, so of course, we don't want to substitute the value of m into the linear equation every time and do all the integration again. So how can we generalize that in the Desmos? Alright, so let's go back to our Desmos. So last time, because I just substitute the value of m as 0.1 into the linear graph, so I've got gx equals 0.1, x plus 3.9. But this time, I'm going to generalize my linear graph. Alright, first of all, I need to create a slide bar for m. Let's say m equals 0.1. Okay. Sorry. Then I'm going to restrict. Oh, sorry, it should be 0.1. What's happening here? I'm going to restrict my value for m from 0.1 to 1.3, and also I'm going to create a step. Step means each time when you move the slide bar, how far you will go. So it becomes 0.1. Okay, so that slide bar, I'm going to place it above my gx function. Then I'm going to create a general form of m. So that's my m, and also my m, 4 minus m. Okay, because c equals 4 minus m, if you still remember. So you can see because my m is 0.1, so right now you will have different, so you still have the same values as before. But if I move my m value, like I move it a little bit, like I move it to 0.2, so you see all the values here, they are different. So let me copy this value. Okay, let me copy it. So that's my area 1. So I'm going to put my area 1 here. So let me make it 4 decimal places. Okay, then I'm going to copy and paste my area number 2 right here. Alright, so I need to be consistent, so that means this one should be 8. And the last one. Okay, so that's my area number 3. I plug here. Good. So you can see if I add area number 1 to area number 3, it still equals area number 2. that means we still have the relationship that as long as the line is in the form of mx plus, that's c equals 4 minus m, then you will always have the green plus blue equals the pink area. Okay, so, and of course you can find the alpha value and beta value as well, but I'm not going to do that here. It's not necessary. All I need to do so is get the area here, and of course you can just copy the decimal point, the value you've got. So let me remind you, your x1 values here, your x2 values just here. So you can copy them into the table. All right, so right now it's m equals 0.2, then I can move on to 0.3, 0.4, 0.5. So you can just see the value keep changing. So let me give you some more dynamic changes of value. So you can see no matter how area 1, 2, and 3 are changing, the sign, the area here, they remain 0. Why? Because as long as the line using that equation mx plus 4 minus m, then the area should be always 0. Is that okay? All right. And okay, so the last thing I want to do is just try to create some visual effects of what actually the area, because right now you could see from the integral how large is each piece of the area, but can we see it from the decimals? Actually you can. Let me just stop that. Okay, let me move it back to 0.1 again. All right, so what I'm going to create is the boundary area in decimals, so you can have a look. Right, so what I'm going to do here is I'm going to create area between fx and gx. Remember, fx is quadratic, and the linear is gx. So what I'm going to do here is I'm going to get fx. All right, so and I'm going to use that one. Okay, twice, and all right, then put something here. Put y here, and put gx here. Okay, so you can see they show you some boundary area. Okay, but what I really want to show you is the area between the for the first part of area 1. Okay, so what I want to create here is something like, okay, okay, so sorry, should be for the area 1, I need to go with gx and fx, right? Okay, and for area 1, remember is form -2 less than x, so that just give you the domain. All right, to x1 if you can. Okay, so you can see there's a tiny bit of area 1. Okay, so because for m equals 0.1 so small, so let me make it bigger. Okay, so you can see that's area 1. Okay, so I'm going to put move that bounded region. So that's for you to show the bounded region below the area 1 integration. All right, so you can see area 1, that's the integral that gives you the value of it, and that shows you the bounded area as actually in the graph. Okay, so you can visualize how the area is changing. All right, and I'm going to create a second area. second area, that y should be, let me, between, so this time's lower than the straight line, but higher than the quadratic. So that's what I'm going to do, is greater than fx but less than gx. And I'm going to do, okay, it's from x1 to x2. Okay, so that will show you the dark part of it, but I don't really like the dark color. Can I change it? Yes, change it to orange. So that's my area number 2. So I'm going to move that. Oh, where should I put it? Sorry, just can't see it at the moment. Okay, I move here. So that's area number 2. So you can see area number 2, the integral, and below that was just the area illustrating the orange color. All right, and the last part is our area number 3. Okay. So for area number 3, and so again, this is higher than the line, so that means y bigger than gx is right, less than fx, but I need to change the domain. So the domain should be from x2 to 4. Okay, and so I move up here. So you can see there are 3 areas now. Okay, so you can see there are 3 areas now. Okay, so I might change the scale so you can look, you have a better look of it. Okay, let me show you like -4 and 2, 6, and have, okay. All right, so you can see the 3 areas. So when I let the line moving, so is the area. Okay, so you can have a rough look. You can see actually the purple area plus the red area always equals to the orange part. So that actually what we require to do for the question, right? Because the question is about getting the 2 area above the line equals the one below it. All right, I think we've done it. So remember, how can you do it? First, you need to create a slide bar for m. Then you change your gx, the linear one, into the general form mx plus 4 minus m. Okay, then you can create the boundary area statement, like gx less than equal to y less than equal to fx, and restrict the domain for a particular area. Okay, then you can have a lovely Desmos boundary area graph, and you can get all the areas here by moving the slide bar, and you can get all the intersection point without doing manual calculation. All right, so that's the part that the Desmos can play in presenting the boundary area, also get you quickly to get the all the values you want, like the intersection and also the boundary area. Yeah, that's it. Okay, so and later on we'll get all the value in the table. All right, so after you've got all the values in the table, then next we can plot the graph of area 2 versus m, and that would, so because we have different m, you have different area 2, so you can see, of course, at 0.2 the area 2 is less than the 1 at when m equals 0.1. So what m will give you the minimum area? That's what we're looking for the next video. Okay, thanks for watching. See you next time.